Hello and welcome to the first lecture of University Physics 2. Now, depending upon where you had your University Physics 1, you may or may not have gotten to the point where you started to talk about springs and simple harmonic motion and periodic motion. A lot of it depends upon the structure of the book, the pace of the course, etc., and so on. So, because that's such an important topic that we actually revisit several times in University Physics 2, and it's also an important topic overall in physics. What I'm going to do with this first series of lectures is to talk about what would approximately correspond to chapters 15 and 16 in University Physics 1 out of the OpenStax books. So, our first lecture, of which this is the first part, is going to serve to sort of summarize some of that with the important details and explain why we're interested. So, that said, this is the first of three lectures for what would be chapters 15 and 16, just sort of stuck together, uh, from University Physics 1. So, that said, the whole purpose, or the purpose really isn't the word. How about the overarching subject that we're interested in this series of lectures? Deals with oscillations, any sort of periodic motion, and especially waves. Now, we've actually seen some examples of oscillations in periodic motion before. Typically, all this falls up under this umbrella term called simple harmonic motion. And a good example of this would be uniform circular motion. So I want to say we talked about that somewhere around chapter 3 or 4 in University Physics 1. And some of the important aspects of uniform circular motion is that the speed is constant. Now, to be clear, that doesn't mean the velocity is constant. Basically, what's happening with uniform circular motion is that you have something going around in a circle at a constant speed. Now, remember, velocity and speed aren't the same, but if you're taking University Physics 2, you know that. So what happens is our v, our speed is constant, and also the length of the or rather the distance from the center of the circle to where the thing is going around, that distance right there is constant. So r, we'd say, is constant. Now, in a situation like this, if you go back and you revisit, say, the chapters that we did on rotational motion, you know that you can talk about this behavior by looking at how the angle with respect to, say, the x-axis here. So we'll say this is x and this is y. How it changes over time. So, and in fact, if your speed is constant, we know that in this particular case, it would be your tangential speed. And since v is equal to r times omega, if r is constant as well, that means that your angular velocity as this thing goes around is constant. So one revolution, one revolution would mean that if you think about the definition of angular velocity, which the average of which is how the angle changes over time. If you think about this, that means that you're sweeping through 2 pi radians once every period. Okay. So this again is angular velocity. University Physics 1 idea. Incidentally, it's also called angular frequency. We're going to see why that is the case here in a moment. This would be, 1 revolution. And t here would be the total amount of time or the period. Now, depending upon where you had University of Physics 1, if they talked about this, they may have called this P. I generally avoid that since it's a time. Now, that said, I want you to imagine, say standing here. We'll say you're standing right here. Apparently, you have some sort of hip issue, and you're sort of looking at, a mass as it goes around. Okay. Now, since this thing is traveling around at a constant angular velocity, what that means is that let's pretend that it took an hour for it to go around once. So if you were to stand there and wait for another hour, you should see it go around and come by once again. And another hour, once again. So if somebody were to ask you, how frequently do you see this mass go by? You'd say, I see it, once every hour. Now, the hour here would be the period of this thing's orbit or the period of this thing's motion. So when somebody asks you how frequently this thing goes by, what they're asking you for from a physics standpoint is something called frequency. Okay, so we use a cursive F for frequency, and you would see it once every period. Okay, so this frequency, this is period. And if you look at the units are 1 over seconds. And in this particular case, 1 over seconds, unlike our discussion way back when in University of Physics 1, in which we saw this dealing with rotational motion, is not radians per second. This is truly 1 over seconds. And 1 over seconds is called hertz, just like the rental car. So, hertz, abbreviated HZ. All right. So what that means is that as long as you're dealing with some sort of simple harmonic motion in which ostensibly the period is constant, is what it means, that you have a relationship between angular velocity, period, and frequency. So your angular velocity is 2 pi again over the period, since it's constant, or 2 pi times f. Now, as a consequence of this, sometimes we refer to omega not as angular velocity, but as angular frequency. And this, is just regular frequency. Now, so what that means is that if you know what the angular velocity of something is, if you know what the angular frequency, quote unquote, is, you have also the regular frequency, and you also have the period as well. So, a little bit of terminology, but more importantly, what I want to talk about next is how examples of simple harmonic motion are related. Now, the three most common ones that you see are uniform circular motion, spring motion, that is in the absence of external forces, and also motion of a pendulum. Okay, so what I'm going to do is I'm going to start with uniform circular motion and show you how the solution to its behavior also satisfies the behavior of a spring and the behavior of a pendulum, which tells you that they're all related. All right, so that said, I want to go back to uniform circular motion again. And I want to think about a situation in which you have, we'll say, a mass going around the center of a circle at a constant speed. So this right here, we'll say, is our r vector. As this thing goes around, we'll have it going around in a positive direction. At this particular instant in time, this would be the direction of its velocity. So here's our mass m. This we'll say is the y-axis. This is the x-axis. We're going to measure our angle theta with respect to the x-axis as we normally do. Since in this case this would be positive motion. So here's r vector, and what I'd like to do is to write down an equation for the position of this thing as a function of time. Now, so this is basically pure rotational motion. And since it's uniform circular motion, what that means is that omega is constant. Now, if you think about what that implies, we know, for example, our angular acceleration is how omega changes with respect to time. Well, what that means is that if omega is constant, that you have no angular acceleration. And as a consequence, if you think about tangential acceleration, which would be how quickly this thing accelerates along the path that it's taking, which is r times alpha, this would be 0 as well. So we're dealing with a situation in which there's no tangential acceleration, no angular acceleration, but there certainly is centripetal acceleration because this thing is staying on a path that's circular. Now that said, if you go back and you remember, the kinematic equations for rotational motion, which look something like this. 1/2 alpha t squared plus omega naught times t. And then omega squared minus omega naught squared is equal to 2 times alpha times theta minus theta naught. So if you go back and you look at these and you think, okay, well, my angular acceleration here is 0. That means that you can sort of clear some of these things out. I'm going to assume that when this thing starts, it starts from an angle of 0 just to make my life easy. And so the important thing that we have here is that, as it says here from our first equation, our angular velocity at any time is the same as what we started off with, which, hopefully is true because, it is constant, right? But it also tells us how our angle is related to that angular velocity and time. So this is how our angle changes over time. But what about our physical position in space? Okay, so that's r. So the r that I want to look at is going to be sort of the ubiquitous x hat plus y hat. We're going to stick with the Cartesian coordinates for the moment. And if you think about that, and you look here at our triangle, we'll say, for r. This would be y, and this would be x. So here, related to the length r, x, y, here's what we have for x. X is going to be the adjacent part. The adjacent part is cosine. So x is going to be r times cosine of theta. Y is the opposite part, or sine. R sine of theta. And theta is omega times t. Okay. So, excuse me. So what we have here is r cosine omega t x hat plus r sine omega t y hat. So this right here would describe the position of this thing as it goes around in a circle. Once again, assuming that our initial angle is 0, and we're experiencing uniform circular motion. Now, what I'd like to point out is that the motion along the x direction, just along x, over time, or the motion along the y direction, just along y, over time, they look like waves. Now, I want to pick on x specifically, just because it has a cosine, and cosines are a little bit easier to deal with because they're even functions. If I were to plot this thing starting off at time t is equal to 0 and put x on the y-axis here and t on the x-axis. So here we are, times t is equal to 0. I would start off, if you plug in 0 here, a distance of r away along the x-axis. So, a distance of r away on the x-axis. Now, if you think about just along x, as this thing goes around, when it gets to this point right here, it is 0 along x. Now, I'm going to try to freehand this. I'm writing on a pad here, so this is going to be a little difficult to do, but we'll try. So you get your standard cosine wave, right? With the bottom part here being r along the x-axis below, or this would be negative r if you want to think of it like that, right? But the important thing I want to point out is that you get what you would call a wave, okay? You would get a wave. And the amount of time it would take for you to go from r along x to cross 0. So r along x to 0 to minus r, back to 0 to r. That amount of time to get from here to here would be a period. Okay? Now, so what you have here, just along the x direction, would be the equation of motion in one dimension, just along x, for a wave that has a height of r, we call that its amplitude, and a period of 2 pi over omega. Now, watch this. So just as an example, like I said, that's uniform circular motion. But let's think of another one that we know of. Let's look at a spring. So we've solved lots and lots of spring problems back in University Physics 1. And the classic example of a spring problem would be a mass attached to a spring, and the whole unit sits on what you would call a frictionless table. So here's a wall, here's a frictionless table, here is our spring that's been stretched, and here's our mass. And what we have done is we have displaced this mass some distance away from the equilibrium position. So this we would call 0. This would be y. We'll say this is x. Here's our mass. Now our spring has a spring constant of k. We've stretched this thing to x naught. And we solved this problem a gajillion times. What I'd like to do, though, is to just look at the spring force. Okay. So when I release this thing from rest, it's going to want to go zing into the left. And it's going to follow a force law that we know as Hooke's law. F is equal to minus k times x. Now the force here is acting just along the x direction. The force is going to act on that mass and cause it to experience acceleration. But look, this is one-dimensional acceleration. And we know acceleration is, how your velocity changes with respect to time. Or, alternately, it's two derivatives of your position with respect to time. Right? So I'm going to plug this in here. I'm going to move this to the right-hand side and sort of switch sides. And if I do that, I get this. I'm going to divide both sides by m. Now, this is the spring equation. Okay, this is also something called a differential equation. Why is it called a differential equation? Well, it's an equation that has derivatives in it. Now, for those of you that go off and take differential equations, and I suspect most of you will, since you're all engineering oriented or science oriented. Basically, what you're trying to do is you're trying to find x, an equation for x that solves this. If I take two derivatives of it, okay, and put that here, then whatever those two derivatives are, plus, in this case, k over m times x itself, that better equal to 0. That solves the equation. That satisfies the equation. Now, here's the deal, though. We have x, or at least a version of x, for uniform circular motion. A uniform circular motion is the same type of motion, simple harmonic motion, as spring motion is, and as we're going to see, pendular motion is as well. Now, the x that we have, if you go back and you look over here, I want to remind you of some terminology that I used. This distance, r, is the furthest distance away, okay, the furthest distance away you can get from the origin. Now, we call that the amplitude, all right? Omega is the angular frequency, all right, or the angular velocity. What I'm going to do is to choose a form. A is the parameter, omega is a parameter. These are things that we would end up finding using this and whatever our initial conditions are. For example, we have pulled this thing 2 meters away and released it from rest. I'm not worried about that right now. What I want to show is that this equation right here, under the right circumstances, actually satisfies this. So let's take a derivative of it. Okay, so A is a constant. The derivative of sine is cosine. The derivative of cosine is minus sine. We have to use the chain rule because we have an omega t in here, and what that's going to do is to pull an omega out. So minus a omega sine omega times t. Let's take another derivative. Here, the derivative of sine is cosine, but you pull an omega out, it stays negative. Now what I'm going to do is to put this in here for this, and put this in here for this. So x is this. So all I did was plug that in for this equation. And the way you would solve this would be to say, okay, well, I don't know what omega is. I don't know what A is. These are going to be things that are going to be given to me via this equation right here and my initial conditions. And like I said, my initial conditions would be I know how far x naught is. You know, that's my initial position. This actually is my amplitude if you think about it. So I already know what A is since A is the amplitude. But if you take a look here, there's a lot of cancellations that happen here. And now I have an equation that tells me what omega is. Now remember, omega is my angular velocity or angular frequency. And in this case, if I solve for it, omega is going to be the square root of k over m. All right. Now, so just as an example, I want you to imagine, we'll say, the spring doing its thing. And, let's pretend that I have a 5 kilogram mass on it, and that my spring constant is, I don't know, how about 250 newtons per meter? So, if I want to find out how long it would take for this thing to make one full oscillation, that would be its period. It is, after all, a simple harmonic oscillator. Okay? The amount of time it takes for it to go around once is going to be the same amount of time that it takes for it to go one full swing. Okay? It starts off at x naught, goes to 0, goes to minus x naught, goes back to 0, and back to x naught again. Starts off at r, goes to 0, minus r, back to 0, back to r again, if you just look along one direction. So, in this case, if you think about what omega is, omega, remember, is 2 pi over the period. So if I want the period, all I do is solve for it. It would be 2 pi times the square root of m over k, since it would be switched whenever I take and I switch places there. It's 5 kilograms over 250 newtons per meter. And if you take and you put this into a calculator, let me do that real quick. Excuse me. I get 0.89 seconds. Okay? So I release this thing from rest. It's pulled, crosses the origin, hits there, comes back in a little bit under a second. All right? Now, so the important thing I'd like to point out is that the x that we got here, which describes this type of motion, is a good solution to this as well. Okay? And what that means is that we can use simple harmonic motion language or uniform circular motion language to describe the motion of a spring. It has an amplitude, it has a period. You can think of it having an angular velocity or angular frequency. Now, let's look at another example. What I'd like to do now is to think about the simple pendulum, which we did back in University 1. Let me just sort of draw my coordinate system here. We'll have the pendulum start swinging from this side. Actually, let me do it this way. Here's our mass. Let me just attach that here. That. Right. There we go. And as this thing swings, it's going to trace along a path that looks a little bit like this. We'll say. Let me just sort of make her a path here. You do it like that. Not perfect, but you get what you get. There we go. So, typically, fix that. Typically this would be the y-axis, this is the x-axis, and what have you. But what we have here is an example of, if you're looking at the behavior of the pendulum and you draw your force diagram on it, you're in a non-inertial coordinate system. So, we have two forces here. We have the tension going up like this, then we have the force due to gravity going down like that. And if you were to think of not using x and y coordinates, but using r and theta coordinates, this right here would be the direction of out from r. And this right here would be the direction of along the positive theta direction. So here's the theta hat direction. This would be the r hat direction. This would be theta. If you think of this as theta right here, the angle between, the y-axis and x, basically. And so if I were to sort of rotate my coordinate system as we've done in the past with inclined planes, and think of this as being r hat and theta hat here, then when I do that, the tension is straight up like that, and the weight is off at an angle like this. And again, we know the angle is theta. So here's FG. And here is the tension like that. Now, what I'd like to point out here is that if you think about what's going on, we'll say in the theta hat direction, that part of the weight that sits in that direction is what's making this thing swing. So in theta hat, what we have here is in the negative theta hat direction, minus FG times sine of theta. Okay. This right here is what's going to cause the mass to experience acceleration. Now, the acceleration right here, though, is going to be, tangential acceleration, right? Because it's along the direction of the circle, along the path of the circle. In the r hat direction, what we have here is we have a negative tension plus the cosine part. That is this part right here of the weight. And those are going to balance each other out. Since this thing stays along the circular path, we're going to call this L. This is the length of the string for our pendulum. And so it stays L away as it swings. All right. Now, so in particular, I want to take a look at this right here. If I go ahead and point out the fact that, the weight here is just m times g, it would be minus mg sine theta is equal to m times a sub t, the tangential acceleration. But look, the tangential acceleration is just r times alpha. And alpha is angular acceleration, which is two derivatives of our angle with respect to time. Okay, so if I cancel the masses out, on the left-hand side, I have minus g times sine of theta. And on the right-hand side, I'm going to have, now r, remember, is the radius of the circle. It's actually L in this case. L times two derivatives of theta with respect to time. Now this is starting to look a little familiar. It's not exactly like the equation that we had before over here, where we had two derivatives of position with respect to time and x. Here we have two derivatives of a position with respect to time, and there's a sine of theta. But we're going to get to a form that looks exactly like what we had before, barring the fact that we're dealing with thetas instead of x's. By noting the fact that the equation that we have here, this is a nonlinear differential equation. They're incredibly difficult to solve. Many times there is no what you would call a closed form solution. They may be intractable when it comes to solving them exactly. But you can make some assumptions with respect to sine. So as long as my theta here is small, now what do I mean by small? Well, I want my theta here to be less than 1 radian. Now, why is that? Well, what I want to do is I want to take a look at sine itself, okay? But I'm going to expand this out in what's called a Taylor series. Now, many of you have started taking Calculus 2, and it's Calculus 2 typically where you see series expansions. But you can, for the most part, write almost any mathematical function that you have as basically a order of magnitude increasing or exponentially increasing sum. And in this case, and this will be something that you do in Calc 2, or you may have done in Calc 2 before, when you actually take and you expand this thing out as a series, it looks like this. It's theta minus 1/6 theta cubed plus 1 over 120 theta to the fifth, and higher order terms. Basically, is out to infinity. And the idea is that if you take and you plug in, if you have an infinite number of terms here and you plug in your theta, whatever your angle is, the right side and the left side will agree. Now, I want to be clear here. This equal sign means equivalent to, it's not the same as. Now, the reason why I want to look at angles that are less than 1 is that if you have something that's less than 1 and you square it, you get a number that's smaller than what you started with. And if you cube it, you get an even smaller number. And so you can see that basically what this means is that as long as my angles are small, I would expect sine of theta to be very, very close to just theta itself, because these higher order terms here we'd be able to disregard. Now, I know it seems funny to say that, but you can actually sort of prove this to yourself that there's reasonably good agreeance as long as you keep your angles small. If I, for example, sort of do a table here with theta on the left-hand side and then sine of theta on the right-hand side, and I did this just for a few. For example, pi over 4, keeping in mind that pi itself is like 3.14 and some change, this is less than 1. And when you do it, it's 0.785. When you actually do this with, sort of goes off forever. But if you take sine of pi over 4, you get 0.707. So close, but not exact. But what about, say something like pi over 8? So if I do pi over 8 on the left-hand side, if you actually do that, it's 0.393. And if you do sine of pi over 8, you get 0.383. So it's pretty darn close. And just, we'll do one more. Pi over 10 would be about 0.314. And if you take sine of pi over 10, you get 0.309. So as you can see, as your angle gets smaller and smaller and smaller, sine of your angle and the angle itself start to converge to become, the same number, at least, out to a few decimal places. So what that means is that I can actually approximate sine of theta as theta for small numbers. And if I do that, I get, in my equation that I had written down there, the following. Okay. And if I just, divide both sides by L, I get this. Now take a look over here. Oops, I don't want to do that, but let me drag this down over here. So you can see the formula is identical. It's just on the left we're dealing with theta, and on the right we're dealing with x. So if it looks the same, that means that the solution, what theta looks like, is going to look like basically what x looked like over here. And now we had tried a solution that looks something like this. And again, if you take a derivative with respect to time of that, you get that. You take two derivatives of respective time of that, you get this. You plug this into this. Oops, I may not do that. So the first one is minus a omega squared cosine omega t. Then plus g over L, theta, theta being a times cosine of omega t. That goes away, that goes away, that goes away, that goes away. So again, in order for this solution to work, omega would have to equal to the square root of g over L. And again, noting the fact that omega is just 2 pi over t for simple harmonic motion, our period is 2 pi times the square root of L over g. Now check this out. The period of our pendulum here does not depend upon mass. So you could quite literally hang anything that you wanted to off the end of this and let it swing. And as long as you displace it the same distance, you let it go, you're going to get the same period. Your period only depends upon the length of the pendulum string and the acceleration due to gravity. Now, I say displace at the same distance, and that's because, we're assuming here that our angle is small. Now, this is the reason why, like grandfather clocks and things like that use a pendulum. As that thing slows down and the angle gets smaller and smaller and smaller, it still maintains the same period. And it only depends upon the length of the rod. Okay? So, for example, let's pretend that the length of your rod was 1 meter. So if that was the case, then the period would be 2 pi times, 1 meter over 9.8 meters per second squared. So if you do that, let's see here. This 1 divided by 9.8. This would have a period of 2 seconds. Actually, 2.01, if you want to be technical about it. So, the point that I'm trying to make, just sort of with this first lecture here, is that any sort of simple harmonic motion, whether it's a circular, spring, pendulum, or as we're going to discover some types of waves, they all sort of look the same, mathematically. And as a consequence, what that means is that these sorts of problems, like spring problems and stuff like that, they actually end up being incredibly crucial in physics itself. One good example of which would be if you think about, for example, potential energy. If you look at a complicated force that has a complicated potential energy, maybe the potential energy looks a little bit like that. So here's your potential energy. We'll say it's a function position. In places like this, you have what looks like a parabola, right? And this right here is what the potential energy for a spring looks like, which means that you can use this sorts of arguments right there to talk about potential energies very close to what you would call equilibria. If you remember, this is where, you take the derivative with respect to whatever, set it equal to 0, and you solve for these are your minima right here. So at these minima, where you have minimum potential energy, small displacements make it act like a spring. Small displacements. Right? So that's it for this lecture. Our next lecture is going to be about the properties of waves. because, like I said, we're going to be dealing with a lot of this oscillatory stuff and wave behavior, as we progress through the semester. And I'll see you then.